Good morning, everybody. Welcome to the class. We'll wait till we get to about 18 people and then I'll start. If you haven't already, please join the Remind for this class. In case I have to move my office hours, it's a good way to oh, someone's right hand rule. Awesome. It's a good way to keep up with me if I have to move my office hours, which I've had to do a couple times for various reasons. Hi, Hazel. Hazel's sitting below me, staring at me. What do you want? What do you want, Hazel? Lay down. Lay down, Hazel. Hazel, come there. Sit. Sit, baby. Good girl. Wow. All right, I think that's enough people. Hello, Courtney. I don't think you're in this class, but hi. Okay. So today we are going to be talking about projectile motion. So projectile motion. Projectile motion deals with things being launched at an angle, okay, and then they go and they land somewhere. All right, so it's projectile motion is sort of inherently two-dimensional motion because you have something moving horizontally and vertically. Okay. One of the things that you need to solve a projectile motion problem is you need to know what is the initial velocity vector. Okay. So let me just review really quickly. What if you have an initial velocity vector where the initial speed is, I don't know, let's say 100 meters per second. Okay. The initial speed is 100 meters per second. And maybe that velocity vector makes an angle of, let's say, 40 degrees with the horizontal. So this velocity vector corresponds to a speed of 100 meters per second. So part of that speed is going up and down, and part of it is going side to side. So we're going to use trig functions to get the components here. Okay, so this vertical component is opposite the angle. So that means that I'm going to use sine because sine is the trig function that has opposite. So this would be 100 sine of 40 degrees. For this, you would want to make sure your calculator is in degree mode because I gave you the angle in degrees. And then for the horizontal component, that's adjacent to the angle, so we use cosine of 40 degrees. So this is going to be, let me plug these into the calculator here. This is 64.3 meters per second. And this one is 76.6 meters per second. All right. So boom, there you go. Now, this is the initial velocity vector. So as the projectile moves, gravity is curving that trajectory. Okay, so the velocity vector does not remain constant. That's an important point. This is the initial velocity vector. So we're going to have basically two equations to describe the motion. We're going to have an x of t, and we're going to have a y of t. All right, so I'm going to start off with the y of t. The y of t is just going to be a kinematics equation, y naught plus v y naught times time minus 1/2 gt squared, where g is the acceleration due to gravity. G is 10 meters per second squared. On all the homeworks that we do, acceleration due to gravity. On all of the homeworks that we do for this class in Canvas, I have it set that gravity is 10, not 9.81, but 10, okay? So I know for most of the assignments I put parentheses use g equals 10, but I'm tired of typing that, so I'm going to stop. So even though it might not say use g equals 10, use g equals 10, okay? So this is the initial elevation. The y naught would be the initial y velocity, so that would be this number if we had that exact launch. And then negative 1/2 gt squared. This is the acceleration term. You can see it's negative because gravity curves the trajectory downward. Gravity accelerates downward. The x of t equation is x naught plus v x naught times time. And that's it. Okay? So the Vx naught will correspond to 76.6 meters per second. Okay, so why is there no t squared term for the x of t? It's because the t squared term corresponds to acceleration, and gravity does not cause acceleration horizontally. Gravity causes acceleration vertically. So there is no horizontal acceleration. Okay? So really, the purpose of today is just to do some examples. All right? So let's do some examples. And we're going to do some more advanced examples than we have before. All right? So let's suppose we have a cliff, like so. And let's suppose that the cliff is 80 meters high. All right. And let's say that at the base of the cliff, we have a projectile that is launched at a speed of 100 meters per second, okay, at an angle of 40 degrees. So it's going to follow this formula, okay? And then there's a second projectile that is launched from the top of this cliff, okay, and this one is launched horizontally. Okay, and we'll say that the horizontal launch speed is 90 meters per second. And these two projectiles are launched at the exact same time, so I will call this projectile 1 and this projectile 2. So projectile 2 is going to kind of go like this, and projectile 1 is going to go like this. All right? And so my question is, how far apart are the projectiles one second after launch? Okay? So to do this problem, what we have to do is we have to figure out what is the x of t and the y of t for both the first projectile and for the second projectile. For this problem, we need to choose an origin. Because these projectiles are starting at different locations, they're going to have different x naughts and y naughts. Okay, so I will put the origin right here at the corner. Okay, so for that first projectile, it has x naught equals 0 and y naught equals 0. So when I type that in here, so for projectile 1, it has x1 of t equals 0 plus 76.6 t. Okay. For its y of t, it's going to have, let's see, its y naught is 0. Its vy naught is 64.3, so I have 64.3 t. And then minus 1/2 g is going to be negative 5 t squared. Okay. For projectile 2, it's not displaced horizontally from projectile 1, so it also has x naught equals 0. So x2 of t is going to be 0 plus, and projectile 2's velocity is 100% horizontal to start with. Okay, so we have vx naught equals 90, and vy naught equals 0. So, and then the y2 of t is going to be, now what is the y naught of the second projectile? Well, it's launched 80 meters above the other one, so it's going to be 80 plus 0, okay, because vy naught is 0 if you have a horizontal launch, minus 5t squared. All right, so now what we're doing, we want to know how far apart they are after 1 second. So I need to figure out what is x1 at 1 second, what is y1 at 1 second. Okay, so if I plug in 1 for time, I get 76.6 meters, and I get, what's that going to be, 59.3 for the first projectile. And then for the second projectile at 1 second, you have 90 meters. And the y coordinate, excuse me, y2 of 1 is going to be 75 meters. Okay? So now we have these 2 points. So we have, if these are our, if this is the origin, the first projectile is over 59 meters, so maybe that's 59 meters, and up 76 meters. Okay? So that's projectile 1. Projectile 2, I did that backwards, didn't I? Gosh darn it. You get, okay, so my point is projectile 2 is maybe right here, and it has its own coordinates. And if we want to know the distance between them, I figure out what is this distance, which would be delta x, and what is that distance, which would be delta y, and I do the Pythagorean theorem, and that's going to give me the distance between them. So what is delta x, the difference between their x coordinates? That's going to be 13.4. That came from just subtracting those two numbers. What is the difference in y coordinate? it's going to be 75 minus 59.3, which would be 15.7 meters. And so the distance between the two projectiles is going to be the square root of 13.4 squared plus 15.7 squared. That'll be the distance between those two, which I will then plug into my calculator. And we get, they are about 21 meters apart after 1 second. All right, so that's a kind of a slightly more complicated problem than we had last year with projectile motion. Okay, so I hope that makes sense. Let me do just a throwback to the type of problem we would have had last year, but I'll add, again, another twist to it. Let's suppose we have that same projectile that we launched horizontally, okay? So we have it launched from 80 meters high, okay? And it's launched horizontally with a speed of 90 meters per second. I did say 90 meters per second, right? Yeah. And it goes like this, and it hits the ground. All right. What I want to know is how fast is it going when it hits the ground? Okay. So I have my x of t. So this is the exact same numbers as the last problem. Okay, so I'm going to just copy over 90t and 80 minus 5t squared. So the first thing we want to do is we want to figure out how much time does it take to hit the ground. Okay, so when it hits the ground, y is equal to 0. The elevation is equal to 0. So we take this equation, we say 0 equals 80 minus 5t squared. And this tells me that it is going to, it's going to be square root of 16, so 4 seconds. It's at 4 seconds, it's hitting the ground, okay? So now what I want to do, if I want to know how fast, that's the speed when it hits the ground. So what I'm going to do is I'm going to take dx dt, and I'm going to evaluate it at 4 seconds. What is the x component of the velocity when it, at the time where it hits the ground? And that would be 90 meters per second. And then I'm going to have the y component of the velocity would be dy dt evaluated at 4 seconds. So dy dt is going to be minus 10t evaluated at 4 seconds. So I'm going to plug in 4 for t, and I get negative 40 meters per second. So basically my final velocity vector goes over 90 and it goes down 40. So this is my final velocity vector. And I want the final speed, so I have to do the Pythagorean theorem on that. So the magnitude of v final is going to be the square root of 90 squared plus 40 squared. Which is about 98.5 meters per second. Now, we could, of course, use conservation of energy. If you remember that from last year, we could use conservation of energy to solve this problem, and it would give the exact same answer. All right? But this is a sort of a pure kinematics way of doing that. All right, so now I'm going to teach you guys about something new with projectile motion, which is something called the trajectory. Okay, the trajectory. So what we have here is we have x of t and y of t. Okay, x of t and y of t. So that is giving us the position as a function of time. The trajectory, on the other hand, is the elevation as a function of the vertical elevation as a function of horizontal position. So it's an actual shape of the path of the projectile through space. Okay? So that's called the trajectory. So it tells you nothing about when it arrives at each location. It tells you just what are all the locations that this projectile goes to. Okay? So how can we get the trajectory? Well, we are going to assume x naught equals 0. Okay? We're assuming x naught equals 0 because so we're assuming that it's launched from x naught equals 0. And then if we have our kinematics equation, x of t equals x naught plus v x naught t, this means that x of t is just equal to vx naught times t. So this is going to actually allow us to solve for time. Okay? That means that time is x over vx naught, just by dividing both sides by vx naught. Then we're going to take this and use it in our y equation, our y of t equation. Y naught plus v y naught times t minus 1/2 gt squared. So we're going to plug this in for time. Okay? So we've expressed time as a function of position. So we have y naught plus v y naught. And instead of writing time, I'm going to write x over v x naught. Like that. Minus 1/2 g x over v x naught squared. So notice how I have eliminated time. So this is now y as a function of x. So this is the trajectory function for projectile motion. I'm going to simplify it. Okay. I'm going to simplify it further. One of the things we can see is that it's a concave down parabola. So the shape of the path of the projectile is a concave down parabola. Vy naught over vx naught. Well, vy naught is just v naught sine of theta, where theta is the angle of launch. Vx naught is v naught cosine of theta. So if I took the ratio there, I'm going to get vy naught over vx naught is just tangent of theta. Okay? So I get y naught plus tangent of theta times x. The x is not in the tangent. This is tangent of theta multiplying x. Minus g over 2 v naught squared cosine squared of theta x squared. So this is called the trajectory function for projectile motion. All right, so that's a new thing that we didn't discuss last year. And it allows us to solve some pretty cool problems. So let me show you. Okay. let's suppose, again, we have that same launch, okay, that we had before. So we have the launch, it was, what was it, 100 meters per second at an angle of 40 degrees. Okay, 100 meters per second at an angle of 40 degrees. But here's the thing. It's not traveling across a level surface. Let's say that this projectile is actually launched onto a hill. So this is a hill. So the projectile is going to go, and it's going to land right there on the hill. So we want to figure out, where is it going to land? So to do that, we need the shape of the hill. All right? So I'll call it the hill function, if you will. So what is the shape of this hill, y of the hill, as a function of x? All right? And so you can see this is a linear hill. So let's just say that the shape of the hill is 0.5x. So it's a linear hill that has a slope of 0.5. All right. We can also find the trajectory of the projectile. So what is the projectile's trajectory? If I put the origin right here, we have y naught equals 0. It's launched at 40 degrees. So I have tangent of 40 degrees times x. Okay, minus g, which is 10, 2 times v naught squared. V naught is 100 meters per second, times cosine squared of 40. That's times x squared. So I'm going to simplify that. 10 over 2 over 100 squared over cosine 40 squared. So this is minus 0.00085, and tangent of 40 is 0.84. Okay, so that's the trajectory function of the projectile, and here's the shape of the hill. So what does it mean for the projectile to land on the hill? Well, that would mean that they have the same position. Okay, so it's basically a collision problem. So we're going to set those two functions equal to each other. Now, I'm always going to give you a hill function, if you will, that makes this equation solvable. Right? This is an easy equation to solve. So solve 0.5x equals 0.84x minus 0.00085x squared. That's an easy equation to solve. But what if the hill function was like rolling hills, for example, where it's going like this? So maybe the hill function is sinusoidal, in which case you would have sine of x equals to a parabola, which you can't solve that equation. You can't write a nice formula for that. You'd have to use a computer to graph the two functions and find the point of intersection. So while I'm going to give you problems that are fairly easy to solve analytically, I just want you to know that it's actually a pretty powerful method where you can use complicated functions in computers and you can get something fairly realistic. All right? I mean, we could even go into if you wanted to computer program a projectile, you know, if it lands, maybe you could have it bounce. How could you have it bounce realistically? You could do all that with the trajectory and figuring out the angle of impact and stuff like that. Okay, so what I'm going to do is I'm going to go ahead and subtract the 0.5x over to the other side, and I'm going to add this one over to the other side. Okay. And then we have, we can divide both sides by 0.34. So actually, I'm going to divide both sides by 0.00085. And we get 400 x equals x squared. X, so we can see there's actually 2 points of intersection between the hill and the projectile. It's launched from the hill. So x equals 0 is a solution. But then we want the solution where x is not equal to 0. So I'm going to divide both sides by x, and I get x equals 400 meters. So that is where the two would collide. All right. So there you have it. I think that's my lesson. I wanted to give you guys a little bit of extra time because these projectile motion problems involve a lot of calculations, and I want to give you enough time to complete those. So that's my lesson, and I will meet you in the Zoom room.